Okay, welcome everybody. So we have learned this morning about symplectic capacities and have seen some of the applications like to dynamics. And now we continue with our wonderful speaker by experience, Sobhan Seyfaddini, who will talk about symplectic Weyl laws and the path to homeomorphisms groups and even further.
Thank you very much. It's a great pleasure to be here at the Institute. I was a postdoc here 8 years ago. Fortunately, I didn't have the chance to come back in between, and so I'm extremely happy to be back here after such a long time. It's also a great honor to be speaking at this event, wonderful event, celebrating the mathematics of Marston Morse. So let's get rid of that arrow. So in my talk, we're going to see two applications of Floer theory, so an infinite dimensional variation of Morse theory, to two questions from the 1970s, which come from outside symplectic geometry. And so this will be kind of a two-part talk. In the first part, we're going to discuss the question of Albert Fathy concerning area-preserving homeomorphisms of surfaces. And the second part, there will be a question of our knowledge about volume-preserving flows on three manifolds. And we will see the Weyl laws that Dan mentioned in his talk, that Dan discussed, play an important role in both of these applications. Okay, so Fathy's question. To begin, I want you to consider the set consisting of all volume-preserving homeomorphisms of the n-dimensional disk, which have compact support, so meaning they coincide with the identity near the boundary of the disk or the ball. Okay? So this set carries the algebraic structure of a group. And it is this algebraic structure that you're interested in today. So in a first course on group theory, one of the first things one learns is that there exists a very distinguished class of subgroups called normal subgroups, which play an extremely important role in determining the algebraic structure of the group. And these are precisely those subgroups which are invariant under conjugation. And the main reason for their importance is that they arise as kernels of group homomorphisms. And so, if you write down a group homomorphism between any two abstract groups, the kernel is always a normal subgroup, and every normal subgroup arises in this way. Okay? So now, what are the normal subgroups of our group of compactly supported, volume-preserving homeomorphisms of the n-dimensional disk? So one immediately identifies two trivial examples, the one-element group and the entire group itself. And the real question is, are we able to identify any other examples of normal subgroups? In other words, is our group simple? Does it have any non-trivial normal subgroups? Okay. And so this question was studied extensively by Albert Fathy in the late 70s. In the postdoc talk, I think I gave here 8 years ago, I mentioned this question. And so here's what Fathy proved. He showed that the group is indeed simple when the dimension is at least 3. Okay, so no interesting normal subgroups when the dimension of the manifold is at least 3. So we see two cases are left out of Fathy's theorem. N equals 1, where the group is just a trivial group, length-preserving homeos of the interval. That's just nothing. So really the interesting case is N equals 2. And the question now becomes, and this is a question that Fathy asked in his paper, is the group of area-preserving homeomorphisms of the 2-disk a simple group? So this is kind of a well-known question, and over the years it was studied by various people in kind of various communities, dynamics, topology, and so on. And maybe in the early 2000s or so, kind of a consensus was formed, at least in the symplectic community, that the group should be non-simple and have proper normal subgroups. And this became known as the simplicity conjecture. So it says, the simplicity conjecture says, area-preserving homeos of the disk is not simple.
Does it matter whether one used homeo or diffeo?
Okay. So the question is about homeos. For diffeos, we will see. You mean area-preserving diffeos of the disk. That's also not simple, but this was already known at that point. We will review the history of the question. But yeah, for the question, it really, this one is, the case of homeos is particularly important. And I'll say why now. This is the case, maybe. Okay, so what I want to emphasize at this point is that this is a purely algebraic question. Okay, so our group carries a natural topology. It's the C0 topology, or the topology of uniform convergence, which is induced by the standard distance in the plane. And as a topological group, it is simple, meaning it has no closed proper normal subgroups. And this fact is not that difficult to prove, and I'm certain it was known to Fatih at the time when he wrote his paper. Okay? And so this topological simplicity of the group already gives you a hint as to why the question is kind of tricky. So imagine you wanted to prove this conjecture. Okay? So the most natural approach would be, the first thing that comes to mind is to write down group homomorphism out of the group into some other group, okay? And if it's non-trivial, you take the kernel, that gives you a proper normal subgroup, you get the conjecture. Okay? But on a topological group like this that carries such a natural topology, and any likely attempt would lead to a continuous group homomorphism, which does not exist in the case of our group, because it has no closed proper normal subgroups. Okay? So this is part of the reason why the question remained open for such a long time. And that brings us to the first theorem of today's talk, which says the conjecture is true and area preserving homeos of the disk. So it's not a simple group. Okay? And this I proved jointly with Dan and Vincent Media around 5 years ago. So we'll see why laws play an important role here. Okay, so the group is not simple. Therefore, it has a proper normal subgroup. I can give you an example right away. Good. So just to simplify notation, I let it denoted by G. Take the commutator subgroup. Okay? So the commutator subgroup, so just the finite products of commutators, it's always a normal subgroup. In the case of our group, it turns out to be a proper normal subgroup. And we will see why that's the case in a few minutes, 10, 15 minutes or so. Okay, so and the proof of this uses ideas from symplectic geometry. Okay, so let me explain how, at least at the first approximation, how symplectic geometry enters the game. Okay, so we saw a brief overview of symplectic geometry. Let me just quickly recall: a symplectic manifold is an even-dimensional manifold equipped with what we call a symplectic form, so non-degenerate closed two form. And examples of these include surfaces with area forms. So our favorite symplectic manifold, maybe for my talk today, is the disk with its standard area. And so automorphisms are what we call symplectic morphisms. So these are those diffeomorphisms that preserve the symplectic structure. And as you could see, in the case of surfaces with area forms, these are precisely area preserving diffeomorphisms of the surface. So we see already a hint as to how symplectic diffeomorphisms enter the picture, but note, symplectomorphisms are smooth. Okay? So when you write down phi star of omega equals omega, you're prescribing a condition on the first derivative of the map. Our theorem, however, is about homeomorphisms. Right? So phi star omega makes no sense. And what I want to do now is explain to you how homeomorphisms arise very naturally in symplectic geometry. Okay. So let's suppose we have a sequence of maps, symplectic diffeomorphisms, phi I, and I have a diffeomorphism phi. I don't know if it's symplectic or not. As a warm-up, let's assume that the phi I converge in C1 topology to phi. Then it's immediate that phi is symplectic, and the proof is easy because, well, being symplectic is a C1 property, hence it's preserved under C1 limits. Now, Gromov asked in the early 70s, what happens if we weaken that C1 convergence to C0 convergence? And the point here is that C0 convergence is supposed to be it's a very weak form of convergence, and a priori you don't expect it to carry any sort of information whatsoever about the derivatives of this map phi. So it's not clear. You would not expect it the limiting map phi to be symplectic. However, one of the miracles of nature is that it turns out to be symplectic, and this is known as the C0 rigidity theorem, which was proven by a combination of results by Gromov and Ilyashberg in the early 80s. Okay. So this is one of the first really landmark results of symplectic geometry and of modern symplectic topology. And over the years, other C0 rigidity phenomena of this nature were also discovered. So in the context of Lagrangian submanifolds, the symplectic capacities that came up in Dan's talk, they also have some sort of a C0 nature, and Hofer's metric can also be viewed from this perspective. So all of this gave rise to what is called C0 or continuous symplectic geometry. We talked about that here around 8 years ago. And so this is a subject that studies such C0 rigidity phenomena and is concerned with continuous analogues of smooth symplectic objects. So the most basic and fundamental notion in the field is that of a symplectic homeomorphism. So we say phi is a homeomorphism phi is symplectic if it can be written as the C0 limit of symplectic diffeomorphisms. So the C0 rigidity theorem from the previous slide says if a symplectic homeomorphism happens to be smooth, it's an honest symplectomorphism. Otherwise, well, we call it a symplectic homeomorphism. Okay. So examples include area-preserving homeomorphisms of surfaces. Okay. And this is exactly the connection between homeomorphisms and symplectic geometry. So this is the connection that allows us to bring tools of symplectic geometry such as Floer theory and Weyl laws to bear on the simplicity question.
Is it obvious those are examples?
Okay, so maybe not entirely. The statement, so there's a lemma one needs to prove that every area preserving homeomorphism can be approximated by area preserving diffeomorphisms. This is known to be true. It was known already probably at the time of Fatih. So that's a lemma. Very good question. Okay, so before I tell you a little bit about the proof of the theorem, I'll spend a few minutes telling you about the history and the motivation behind the simplicity question. So first, motivation. I mean, there are actually lots of different motivations, and different people arrived at the simplicity question with different motivations, but I've picked one that can be explained in 2 minutes. And here's one. So comes from this kind of overarching principle that's omnipresent throughout geometry, that we try to understand geometric objects by studying their symmetry. And so the idea here is that the algebraic structure of the symmetry group is supposed to encode information about the underlying geometric object itself. Okay. And so I believe this goes back to Felix Klein, and we could maybe examine this idea here in one particular setting, where the geometric object is, let's say, topological manifold, and then the symmetry group will be homeomorphisms of it. Here's a theorem. Suppose you have two manifolds M and N, then any group isomorphism between the homeomorphism groups of the two manifolds is actually induced by a homeomorphism between the two manifolds themselves. So you see that the algebra of the symmetry group fully recovers the underlying geometric object. And the same phenomenon is actually true in other categories. So it's true for CK diffeomorphisms, volume preserving, symplectic, and contact categories as well. So that's one motivation.
You're in the compact manifold case.
Let's say it's compact, but I think it's true. It's just in full generality as far as I know, but I don't have the proof from my mom.
So you have to sort of stick in the same category, otherwise in the open interval and the closed interval.
Okay, so let's say compactly supported homeomorphisms of a manifold. Yeah. Okay, as for the history of the simplicity question, it has actually a very long and rich history. So it goes back at least as far as early 1930s, when it was posed for homeomorphisms of the n-sphere by Ulam in the Scottish book. So as you could see in this photo, was problem 29 in the Scottish book. This particular photo was taken by Joseph Teichmann, who's the department head at ETH, last August in the Scottish Cafe. So they keep a copy of the book, and Joseph was there, and he took this photo and sent it to me. So the cafe now is in the city of Lviv, which is currently in Ukraine. At the time, it was in Poland. Okay, so the cases n equals 1 and n equal 2 were solved by Ulam, Schreier, and von Neumann. But kind of real progress towards this question came several decades later, in the 60s and 70s, where there was a flurry of activity surrounding the simplicity question for various transformation groups and all sorts of manifolds, and lots was proven. For the sake of simplicity, I summarized the case of the history of the disk, the history of the disk, the history in the case of the disk. Okay, so homeomorphisms and diffeomorphisms of the disk in any dimension are simple groups. Homeomorphisms, volume-preserving homeomorphisms and volume-preserving diffeomorphisms are also simple groups when the dimension is at least 3. We saw that the case of homeos was Fatty's theorem. Now, so the remaining case from the list here is that of dimension 2, and this is where area-preserving homeos and diffeos in dimension 2. That's where the situation changes. Area-preserving diffeos of the disk is not simple, and area-preserving homeos of the disk is also not simple. The reason for this seems to be some obstructions that come from symplectic geometry that gives us proper normal sums. We will see both of the reasons for both of these, actually, for area-preserving diffeos and homeos. Okay, so with that said, I will now kind of briefly give you an overview of the proof of non-simplicity in the case of area-preserving homeos of the disk. The initial solution that we discovered with Dan and Vincent Millier used ideas from large-scale geometry of Hofer symmetric. However, the solution that I'll present to you is a later solution, which we discovered, again, Dan, Vincent Millier, Chukyumak, and Ivan Smith. And the reason I've chosen this later solution is because it has a very nice connection with what's called the Calabi invariant. This is where you see exactly where the Weyl laws come in, and also it has an application in the second part that we will see. So the Calabi invariant. Okay, so the Calabi invariant is actually a group homomorphism, sometimes called the Calabi homomorphism, from area-preserving diffeos of the disk to the real one. So it takes as input an area-preserving diffeomorphism, output is a real number defined in the following way. So it's known that area-preserving diffeos of the disk is path-connected. So I take an isotopy in the group, a path in the group connecting the identity to my area-preserving diffeomorphism F. And I'll pick 2 random points in the disk and consider the vector that connects x, say x to y. Then as you follow this vector throughout the isotopy, the vector makes a certain amount of turn by some angle, which I'm denoting by angle sub f of x comma y. Okay? And the Calabi invariant is defined to be the average of this angle function over all pairs x and y. Maybe it's not obvious why it's well defined. Maybe it's not obvious why it defines a homomorphism, but I won't prove any of that. I'll just put it on the slide. So we should think of the Calabi invariant as an average rotation number. It can be checked that it doesn't depend, this definition is well defined. It doesn't depend on the choice of the isotopy FD, that angle function is integrable, there are no problems along the diagonal and so on. And moreover, it defines for us a group homomorphism. So in particular, it implies area-preserving diffeos of the disk is not a simple group because we could take the kernel.
Even with topology, even as a topological group.
Yes, it's so with this, it's continuous in the C infinity or C1 topology, right? The case, it is different here, the story.
Is there an analogue for vector fields also? To infinitesimal homeomorphism?
Say again?
Is there an analogue for vector fields or infinitesimal?
Infinitesimal. So no, not that I can think of. I mean, you can't differentiate a path of homeomorphisms.
You can look at the rotational of a vector field, things like, you can look at rotational of the vector field, integrate, I don't know. Or you can
You're trying to construct the Calabi invariant for homeomorphisms. Okay, that's the next slide.
sorry.
Okay, we'll get there. Okay. By the way, I don't think this is the original definition of Calabi. I believe, I learned of this from a paper of ETH-Zürich, who's here with us today, but I believe this is due to Albert Fati, this description. Okay, so now let's take a look at where we stand with regards to the simplicity question. So we have area-preserving diffeomorphisms. We know they sit inside area-preserving homeomorphisms densely with respect to the C0 topology. You have this beautiful homomorphism defined on a dense subset or a dense subgroup of our group. So the natural question that immediately pops in mind, which was already in your mind, is can we extend it? And this question actually was already in Fati's paper. It resurfaced over the years. It was mentioned by O, and it also appears in a talk that I find very inspirational by Etienne, titled Knots and Dynamics. Okay. We will see this Knots and Dynamics talk comes back again and again in the talk. And the reason for this is obviously clear at this point, because if the answer is positive, then you take the curve, and we're done. Okay. Here is some evidence for why the answer might be positive. I learned of it actually for the first time from that Knots and Dynamics lecture. Suppose you have two area-preserving diffeomorphisms, G and H, and let's suppose the two are conjugate to one another via an area-preserving homeomorphism. So not necessarily conjugate as diffeos, but as homeos. If Calabi is to extend to homeos, if there's any hope of that, the two had better have the same Calabi invariant. And the answer to that is, that turns out to be the case. And this was proven by Gambardou and Gis in 97. Okay. So that gives us a glimmer of hope, this topological invariance of the Calabi homomorphism. Okay. But there are some problems. Okay, so let's see what the problems are. I mean, if you try to approach it kind of the most straightforwardly, which is just take C0 limits and use density, you run into problems because Calabi is not continuous in the C0 topology, and that's not very difficult to see. So we recall Calabi is an average rotation. So if you take a diffeomorphism or a homeomorphism, which concentrates a huge amount of rotation near a point, then that shows you that the Calabi invariant is not C0 continuous. So you have to look at storm in the eye to see the C0 discontinuity. Okay, but there's actually an even bigger problem, which I mentioned earlier, that our group just doesn't admit any continuous homomorphism. So it's not just the problem that the Calabi invariant is not C0 continuous. There's just no such thing whatsoever. So maybe it's not clear. Yes.
What's the story behind the large rotation near a point picture again? You were
so this is like a storm. This is a painting that Etienne used in his Bourbaki talk on the subject. It's I think it's I forget the name of the artist, but it's on the cover of this book by Edgar Allan Poe, staring the maelstrom in the eye, something like this. And so you should think of this as an area-preserving map of the disk that's rotating super fast. This is the center of the disk. And so things are rotating super fast near the center. So you have a huge amount of rotations concentrated near the center of the vortex. And that's what leads to C0 discontinuity.
that much.
Yeah.
More wondering about the poem.
Oh, where the photo came from. Yeah. The first time I saw this photo used to explain the C0 discontinuity of Calabi was when Etienne used it in his Bourbaki. But it's a perfect fit. Okay, so it turns out it does admit extensions. Okay, so this is what we proved with Dan, Chu Kumag, Ivan Smith, and Vincent Millière. We showed that the Calabi invariant not only does it admit one extension, it in fact admits infinitely many distinct extensions. Okay, so which I'm denoting any given one by Calabi overlap.
Uncountable.
Uncountable.
Maybe you could mention that none of them is measurable.
None of them are measured. They're all about
That's striking.
Yeah, they're about as uncanonical as this. So the axiom of choice enters the picture. We will see why there are so many.
And you use the axiom of choice for just not simple.
No, you could avoid the axiom of choice if you want non-simplicity. Okay, I'll comment on the axiom of choice in 2 seconds. I could do it now, but let me it'll appear here, so I'll comment on it there. So, okay, so the first comment is that, okay, so we got the simplicity conjecture. You take the kernel of any one of these guys. This example I explained at the beginning, that the commutator subgroup is a proper normal subgroup. We get that as well, because you have a group homomorph, any of these is a group homomorphism into an abelian group. So the kernel contains, which is a proper normal subgroup, contains the commutators. Okay. And okay, lots of extensions. Many of them have different kernels. So we get, in fact, uncountably many, lots of normal subgroups. And so the reason for this is exactly the axiom of choice. So can the axiom of choice be avoided? The short answer is no. And the reason is this. There are models of set theory in which, without the axiom of choice, in which any group homomorphism from area preserving, you could prove the following fact. Any group homomorphism from area preserving diffeos of the disk, area preserving homeos of the disk, to the real line must be continuous in those models. So in those models of set theory, there are no real valued extensions of.
No, but it still possible it's one could prove simplicity.
Yes, you will see. Yes, the simplicity will come down. Yeah. So there are no real valued extensions of Calabi, but there are non-real valued extensions can be constructed. I don't think we'll get to that, but non-real valued extensions can be constructed without the axiom of choice. And if you avoid the real line, and then you get actually a canonical natural extension. Okay, outline of the argument. So let's see why the Calabi invariant extends. Okay, so here are the key ingredients. So we use a form of Floer homology. We call the one we use in the paper, we call it a quantitative Heegaard-Floer homology. So it's a variation on Heegaard-Floer homology to define the spectral invariants that we call now Cn. So these CNs, there's a sequence of them, one for every natural number. They eat area preserving diffeomorphisms and give you back real numbers. Now, in the paper, as I said, we use this Heegaard-Floer homology, but you could also, now we know we could also use spectral invariants that come from periodic Floer homology, which Dan mentioned. So you could take these really to be those invariants from Dan's talk. Now, they are useful because they have the following properties. So they're not group homomorphisms, but they are what we call quasimorphisms, which means they satisfy their group homomorphisms up to a bounded error. So they satisfy inequality of distance. In the case of our invariants, we showed the nth invariant has an error of 1 over n from being a group homomorphism. Okay, so we will see this is important. Obviously, there has to be a connection between these invariants and the Calabi invariant if we want to extend the Calabi invariant. And the connection comes in the form of a Weyl. Okay, so the Weyl law in this particular setting gives us the following statement. You've taken area preserving diffeomorphism phi, look at the asymptotics of these invariants. What you see in the limit is the Calabi. Okay? And this is where the miracle of Floer, one of the miracles of Floer theory. Even that first line is, I think, a miracle of Floer theory. And okay, so everything on the screen so far is about diffeos, so there must be something about homeos. Otherwise, I can't say anything about homeos, and that comes in the form of this last property. These invariants turn out to be continuous in C0 topology, and we can extend them to area-preserving homeos of the disk. Mm-hmm. So there will be. There were obstructions to constructing continuous homomorphisms, but there are no obstructions to constructing continuous quasimorphisms. And so this is proven with techniques from C0, symplectic geometry, and surface dynamics. And I claim these three properties. What you see on this slide is enough for extending the Calabi invariant. And we will do that on the next slide. So we'll take these three properties and extend the Calabi invariant. Okay, so first, we are going to construct a group homomorphism into a more natural abelian group for our context, okay? And the abelian group is actually a vector space, is the set of real valued sequences modded out by sequences converging to zero. Okay? And here is our initial group homomorphism. So I call it curly C. It takes an area preserving homeomorphism and it associates to it the sequence given by the invariant Cn of phi, or the equivalence class in this quotient vector space. We've already used the third property, the continuity property, because to even write down that sequence, I needed to know that those Cn's could be defined for homeomorphism. So the third property got used already. The quasimorphism property tells us that this curly C is a group homomorphism. Okay, so I won't go through the details of the proof, but remember that the Cn was at distance 1 over n from being a group homomorphism. In this quotient space, that translates directly to this map C, curly C being a group homomorphism. And okay, so 0 and 1 tell us we have a group homomorphism. 2 tells us, connects it to the Calabi and tells us a group homomorphism is non-trivial. So if I restrict this group homomorphism to diffeomorphisms, then the sequence I get for each diffeomorphism is the Calabi invariant of that diffeomorphism. And this comes from the Weyl, because Cn of phi converges to the Calabi invariant, this quotient space, this is what you get. Okay, so we already got what you wanted, which is to avoid the axiom of choice and get the non-simplicity. So non-simplicity at this point we have, because you have a non-trivial group homomorphism. And now if you want the axiom of choice, if you want an extension of Calabi, then you pick a homomorphism from this vector space curly A to the real line, which sends the constant sequence to the value of that constant itself. This is where you have to use the axiom of choice. You have to use the fact that this vector space admits a basis. Okay, and once you have this, you compose it with curly C, and that gives you an extension of the Calabi there. Okay, and okay, so and you get one for every choice of basis or every choice of projection.
But how do you know that they're all independent?
That they're not the same.
Right.
I mean, you just have to pick this projection so that they're different. You know, the way it works is that you pick a basis for that vector space A, such that there you need to pick a basis. That's where you use the axiom of choice, and you pick it such that the first element in the basis is the sequence 1 1 1 1 1. Then the projection just you write down any element in the vector space.
Aren't you worried that it all lies in a finite dimensional space?
Maybe just say that it's actually a surjection.
Yeah, this is a surjection. Okay, now I understand the question. Right. Thanks, then. Great.
That
answers the question. Okay, thanks. Seriously, the question.
I guess instead of using a base, you can use some ultra filter and
so what with the ultra
if you
filter?
choose an ultra filter finer than n bigger and bigger, then there will be a limit for each ultra filter. It does not show that there are many.
Okay, yeah.
But instead of choosing a base in a big vector space,
I could have chosen an ultra filter. Okay. Okay, so we're done actually with the first part of the talk. Are there any questions? Because now we're going to switch gears and look at something else.
So if you take just a rotation of the disk, it will not be a commuted.
No, yeah, that's something that was not obvious, right? If you take compactly support, it should be compactly supported, but anyway,
Yes.
you could take a rotation of the disk
And slow
and slow it down.
Yes.
And it's not, up until this point, it was not clear whether that can be written as a commutator of homeomorphisms or not. Now we know it cannot. Actually, this, you won't see this, but this plays an extremely important role in the proof of what's coming in the second half of the talk, this fact that you just pointed out. Okay, so what have we seen so far? We saw that the Calabi invariant admits many, many extensions from area preserving homeos of the disk to the real line. And now what we're going to see in the second half of the talk is an application of this to a question in fluid dynamics, which was posed by Arnold in 1973. And all of this is based on, the second half is based on joint work with Oliver et al. Okay. So now, Arnold's question, so now we're going to change gears and go to dimension 3. Arnold's question concerns a quantity associated to volume preserving vector fields called helicity. It is defined in the following way. Consider closed three manifold equipped with a volume form, which from this point onward, I will denote by letter mu. And for the sake of simplicity, I'm going to assume that the three manifold is the three sphere. Okay. This assumption is just to make my life simpler here. It's not needed for the definition of helicity, nor is it needed for the results I'm about to state. Now, suppose you have a divergence-free volume-preserving vector field on the three manifold. Then since the vector field is volume-preserving, the two form obtained by plugging the vector field into the volume form is closed. And since the manifold has no second cohomology, this closed form has to be an exact form. So I have a primitive alpha. And using this primitive alpha, you can define the helicity of the vector field x, which is defined in terms of this formula you see on the screen. So we take alpha, the wedge product of alpha and d alpha. That's a three form. I can integrate that over the three manifold. A real number I get, and I call that the helicity of the vector field x. And it's not difficult to show that this quantity is independent of the choice of that primitive alpha. So it's a well-defined quantity.
Can we give some physical picture of what it means?
I think we will see, because we will see in a couple of slides. There's a description by Arnold that I think I find more appealing. I'll say where it comes from. So here's the property of helicity, which is really crucial for the second half of the talk, is that it is invariant under the action of volume-preserving diffeomorphisms. So if you have a vector field x and look at this push forward or pull back by a volume-preserving diffeomorphism, then the resulting vector field has the same helicity. And it's not difficult to see because, well, if you replace x by f star x, the effect on this primitive form alpha is that it gets replaced by f star alpha. Plug that into the formula for helicity, and just simple symbol manipulations will lead to helicity of x being equal to the helicity of f star x. So this invariance of helicity is kind of the key concept in the second half of the talk. Now, one motivation for studying helicity, for its importance, it arises as a conserved quantity in many important physical systems, such as those arising in magnetohydrodynamics, fluid dynamics, and in fact, it was in these contexts that it was first introduced in the 60s by physicists. And so I'll explain to you this helicity conservation in the context of fluid dynamics. So let UT be the velocity field of an ideal fluid. So it's a time-dependent vector field, and it's supposed to solve the 3D Euler equation, say on the sphere. I assume it stays smooth for all time. Okay. Then you could associate to this vector field a second vector field called the vorticity. So it's just the curl of the velocity vector field. So you get another time-dependent vector field. Helicity conservation says that helicity of the vorticity vector field is independent of time. So in this sense, you get a conserved quantity for solutions to the Euler equation. As you could imagine, fluids people are quite excited about having conserved quantities for they're fluids. Okay. Now, our story with helicity begins with a paper of Arnold from 73, in which he derived the following ergodic, more geometric description of helicity in terms of linking numbers, or asymptotic linking numbers, which I'll summarize for you on this slide. It's a very beautiful paper by Arnold. So let X be a volume-preserving vector field, and let's consider its flow phi t. I'll tell you what the helicity is in terms of linking numbers. So we picked two random points again, P and Q in our three-manifold Y, and two moments in time, S and T. And what I do is follow the orbits of P and Q for times S and T respectively. Okay? So I get two orbit segments, and we want to define the linking number between these two orbit segments. Okay, so they're not closed, but what Arnold said we should do is close them up by adding geodesic segments. So you take you pick a Riemannian metric and use geodesics to connect the endpoint to the initial point. You get two loops, take their linking number. That's what I'm calling LK of PQST. So it's linking of the orbits of P and Q up to times S and T. Okay. Now, what we really want is the asymptotic linking number between the orbits of P and Q, which is naturally defined in terms of the formula you see on the screen. So you take the linkings of the orbits of P and Q up to times S and T, and then divide by S times T, let time go to infinity, and you get the asymptotic linking number between the two orbits. You could show that the limit exists for almost every pairs of points P and Q, and moreover, this asymptotic linking number is integrable. So you have an integrable function. What do? You take its integral. Okay. So we take its integral, that's what Arnold did, with respect to variables P and Q, and miraculously, this coincides with the helicity of the vector field. Okay. So this beautiful description is what Arnold discovered. So we can think of helicity as an average linking number, the average asymptotic linking number between pairs of orbits of our vector. Okay, so having derived this formula, we get to Arnold's question now. So let's just keep in mind we have two formulas for helicity, one in terms of differential forms and the second one in terms of asymptotic linking numbers. And here is Arnold's question. So it has two parts. The first part I'm calling invariants, and here's what it says. So let's suppose you have two vector fields, x1 and x2, volume preserving vector fields. And let's say it happens that the flows of these vector fields are conjugate to one another, again, via volume and orientation preserving homeomorphism. Probably guess what he asked. Do the two vector fields have the same helicity? And so if F is smooth, then that's the invariance property I showed you two slides back. Okay? But for a homeomorphism, this is not obvious. And then the second part of the question is what I call the extension part of the question. Imagine the answer to the invariance part is yes. Can you then extend helicity to volume preserving flows, which are only C0 and no longer smooth? So there's no vector field to play with. So obviously, if you want an extension, you'd want that extension to be you don't want it to be a silly extension, like say, the usual helicity for smooth things and 0 for anything non-smooth. You'd want it to be at least have some nice properties like invariance. So the extension part is supposed to be, affirmative answer to the extension part is supposed to be strictly more difficult to get to than the invariance part. So let's take a closer look at Arnold's question and see what are some challenges if we try to approach it directly. So if you use the classical definition of helicity, so in terms of differential forms, and try to replicate the derivation I gave for invariance 2 slides back in the case of diffeomorphisms, at some point you have to pull back. You'll have to write down F star alpha for a homeomorphism. So that's a problem. That's where this strategy stops. But we have this Arnold strategy, which is involves asymptotic linking numbers, this Arnold formula. And let's examine that in the case of at least invariants. So let's recall this asymptotic linking formula is defined in terms of linkings of loops, and linking numbers of loops is invariant under homeomorphisms. So again, this gives you a glimmer of hope, as did the case of invariance of Calabi for the topological invariance of Calabi. Yeah, I guess I should have remarked, sorry, before I come back to this. I mean, you should think this is quite analogous to the sort of things we did with the Calabi invariant, but now we're doing it for helicity. Okay? But the context is quite different because now we're looking at volume preserving vector fields as opposed to area preserving maps of surfaces. And here, the sort of rigidity that was there is not present. So even invariance is not known. Okay, so going back to here, we see, you know, the linking numbers are invariant under homeomorphisms, but if you try to push this further, you notice that you run into a problem with these geodesic segments, right? This map F, even if it's a diffeomorphism, it sends these geodesic segments to segments which are no longer geodesics. So then that introduces error terms in that asymptotic linking, in the linking numbers. If F is a smooth volume preserving diffeomorphism, then you can control those error terms, bound them by norm of the derivative. In the asymptotics, they actually vanish, and you get a new proof of invariance of helicity for under diffeomorphisms. But for homeomorphisms, there's just no controlling. A homeomorphism could really entangle these geodesic segments so badly, there's no controlling of those error terms. Okay, so that's where this strategy runs into trouble. And of course, if invariance is not easy to get, then extension is even more difficult to get. And here again, that vortex picture tells you what sort of thing can go wrong. You could have large asymptotic linking number concentrated, say, near one periodic orbit. So just imagine a periodic orbit and then nearby orbits linking really fast around. They could link so fast that the asymptotic linking number will blow up. And so badly, it will no longer be L1, and you won't be able to write down Arnold's formula. This picture, again, as in the case of Calabi, also tells us that helicity is, by the way, not continuous in C0 topology.
You need some kind of pattern on the infinity. L would be good enough for the argument. Pathwise linear or
I think so. If you put some sort of regularity on the vector fields, you get it. Maybe I should have mentioned, actually, now that you mentioned this, so for example, in the case of the Calabi homomorphism, I forget now, I think this was due to Fathy, he showed, for example, for Lipschitz homeomorphisms, the whole thing works. So here I expect the same would work. Okay, so some history and motivation behind the question before I tell you some of the results. So this is also, after being posed by Arnold in 1973, it's resurfaced in the works of several people, including Gessen, Gambado-Gis, Muller-Svet, and also appears in that knots and dynamics talk that I mentioned by Etienne Gis. And the reason for this, part of the reason for this is a quite natural question from a dynamics perspective. You have an invariant for smooth dynamical systems. It's very natural to wonder whether you could extend it to C0 setting or more generally in low regularity setting. And this perspective also is one motivation from the point of view of fluids. So Terence Tao actually has a blog post. It's about that knots and dynamics talk, in which he mentions, he gives the following perspective on the Arnold's question. So you could imagine you have a fluid which started off by being smooth. Over time, it develops singularities and becomes non-smooth. So past the point of singularity, you can no longer make sense of helicity as a it doesn't exist. You lose that as a conserved quantity. However, if the answer to these questions turns out to be positive, then it could potentially give you a conserved quantity for singular fluids. We'll see there's a funny twist to this on the next slide. There's been some recent developments in the fluid dynamics community kind of related to this. Okay, so here is our result on helicity. So as I said, this is joint work with Oliver Ettmeyer, and it's quite recent from August. So we showed that the answer is yes to the invariance question for vector fields which have no zeros. I'll comment on that in a second. Okay. The answer to the extension question is also positive for C0 flows which satisfy the following two conditions. The first is that they have no rest points, so that's just analogous to vector field not having a zero. And here's the second condition that says the flow should have no periodic orbit of positive measure. So let me comment on the hypothesis. The no zeros or no rest point hypothesis. We will see, I won't be able to go into much detail about it, but on the next slide, we will see it comes up. But if I had to say, three phrases on it, I'd say when the flow lines of a non-vanishing vector field or if, the flow lines of a flow without a rest point, it gives you the structure of a foliation. And that structure of foliation is used heavily in our proof. Okay, so that's what the no zero assumption buys us. As for this no periodic orbit of positive measure, so the reason for this assumption is as follows. The C0 world is quite wide. There exist volume-preserving flows on the 3-sphere with a periodic orbit that takes up 99% of the volume. Okay. This sort of pathological situation you want to avoid, and we do so with that hypothesis. So not only is this natural from, say, the physical perspective, because I have a hard time imagining a fluid with this kind of behavior, but also I cannot say this with certainty. I suspect the answer might actually turn out to be different, might be negative without this assumption. There might be no interesting story to tell. Okay, so perhaps it should have been posed in the first place, but I'm not entirely sure. Okay. So
I have a question.
Yes.
So is there an analog of this? There's a theorem by Oxtoby and Oolong that says if you have no atoms, then you're homeomorphic to a volume preserving network.
Right.
Is there an analog for flows?
So we use this example that I mentioned, you could construct it using the Oxtoby-Oolong theorem. Yeah, you could take the Hopf flow, like the nicest flow, take a periodic orbit and put take a measure on the space that has like half the Lebesgue volume plus the measure supported on the periodic orbit. This has no atoms by Oxtoby-Oolong. It's equivalent to the usual measure. So you take a conjugation, it gives you a flow on the sphere where that circle gets sent to something with half the volume. So the Oxtoby-Oolong theorem actually plays a role here. Okay,
I was confused. Is it you need both or any one of two?
No, I need both. With no rest points, no periodic points of positive measure. Both assumptions are.
And you think if you had a periodic orbit of positive measure, it just might not be true.
Yeah.
So you think if it has no periodic orbits of positive measure, but could have rest points.
That's an interesting question. So we do have some results that we think we can go further, but to full generality, we don't know how to go there yet, or maybe never. We had some exchanges with Boris Hessen about this. I don't know, his perspective from this conversations, it was not really clear to us whether it might just fail to be true in full generality, but I can't say for sure. Etienne has thought about this question.
I may comment that the theorem of Arnold giving the interpretation of linking numbers has been criticized in the case of vector field with zero. Some people claim that the proof of Arnold is not correct if there are critical modes.
Oh my God, okay. I know that proof had some problems because that picking those geodesic segments is a serious subtlety that was only settled by Vogel.
Precisely with the zeros of the vector.
Okay. Okay, so maybe it doesn't, so maybe what we think we can do cannot be done. And that's a future project. It's not here. Okay, thanks for that input. Okay. So some past results. The first result that I know of in this direction is the result of Gambado and Gis from '97. which proves invariance for vector fields which arise as suspensions of area-preserving maps of the disk. If you take suspension of an area, so you take an area-preserving map of the disk, you look at its mapping cylinder, right? On that, it induces a vector field, okay, this vector field preserves a natural volume. There's a connection with the Calabi invariant here.
So the helicity is the Calabi invariant?
In this case, yes. Yes, the short answer is yes, up to some technical. Yes. And so what Etienne and Jean-Marc Gamado proved, which I mentioned earlier, that said Calabi is invariant under the action of area-preserving homeomorphisms, then implies this. Is that right? That's how you get it, if I remember correctly. Okay. We will see this connection to the Calabi invariant come up in the next slide again. So Muller and Smith proved it for invariants for vector fields which preserve the contact form. So they had the idea of applying C0 contact geometry to this. And as far as extension was concerned, there was no progress until recently. And then here's a funny twist. So Geary, Kwan, and Novak, these guys, the three of them, they are fluid dynamicists, and they have a work in progress that's supposed to appear on the archive very shortly. I know of this because Geary and Kwan are at ETH, so they're my colleagues there, and I talked to them about it. Here's what they did. They construct an extension of helicity, which I'm denoting by H bar, but in a different spirit. They constructed at the level of vector fields. So ours is constructed at the level of flows, but they constructed for vector fields which are very, very irregular. Okay. So, and then here comes the surprising, even more surprising part is that they construct a weak solution to the Euler equation using convex integration theory, H principles, for which helicity conservation fails. Okay. So it looks like it goes exactly the wrong direction. And so it looks like it directly contradicts our result. Okay. So the first time I heard about it, I panicked a little bit. The Quantum magazine is going to make fun of symplectic geometers and fluid dynamicists. But I was, so all of us actually, Geary, Kwan, Etmar, and I, we were all recruited at ETH recently. My other thought was that the president of ETH will come and say, what are you guys doing? But okay, the explanation, there is a clear explanation here, which hopefully stands the test of time. Well, theirs is defined for vector fields. These vector fields, they're extremely irregular. The domain of this even includes vector fields which are not even h-1/2, and that's the case for this guy. And so they don't have flows. There's no meaningful flow you could attach to these vector fields.
So the n means it should be a not n? X not in h-1/2 or x in?
X is in h-1/2. So divergence of three vector fields that are this class of irregular vector fields, which are h-1/2, is contained in a domain. But the domain contains some other stuff too. I cannot claim I understand their work.
That's horrible stuff.
Yeah, but they say our stuff is horrible because our flows. So, okay, so this doesn't fall under the domain of our extension, but our extension is for C0 volume preserving flows. They don't even have vector fields in any sense. So there are two extensions in different directions, but yeah, these guys don't have a meaningful flow. Ours don't have vector fields. So if you do things differently, I guess you did different answers. Okay, so hopefully no contradiction here. And okay, so as for, okay, I don't have much, there's one slide left. I can't go into much detail about the proof, but I'll say a few words of how we connect this to the Calabi invariant, the first part of the talk. So the challenge here, one challenge here is, at least from the perspective of a symplectic geometer who likes to play with Floer theory, is that there is no Floer homology for volume preserving vector fields. So you don't have those spectral invariants, no Weyl. It's not possible to replicate that strategy you had for the Calabi invariant. And the goal here is to connect the story to the Calabi. Okay, so I will explain to you how helicity, I kind of already alluded to it. We will see how helicity connects to the Calabi. So to explain this, first some notation, let's consider the cylinder, so 0, 1 times the disk. On this, you have the standard volume form, so dx dy is the area form, the standard area on the disk, and dt is length on the interval. And on the cylinder, you have this, the trivial horizontal flow, which I'm denoting by phi 0 superscript t. So this is volume preserving. And it turns out it's a bit of a lemma that one needs to prove. For the class of volume preserving flows we are considering, this is a local model. So it gives you a flow box, or a flow box near every point. You have a flow box that looks like this. So here you really have to use that phi t is a C0 volume preserving flow with no rest points. Otherwise, there's no flow box, and no periodic orbits of positive measure is needed. Otherwise, this is false. This statement is false. Okay, so let's take your flow box. So I've drawn a flow box for you on the screen for our flow phi t. And so inside the flow box, the flow is trivial, it's horizontal flow. Suppose I'm given this flow box, the data of a flow box, and also a second piece of information, which is an isotopy, a path in area preserving homeos of the disk. That's what I'm denoting by ft. Then, given these two pieces of data, I can take my volume preserving flow and modify it in the following way. I go inside the flow box, the flow lines look trivial. I'll replace them with the flow lines of this area preserving isotope. And so a typical point here is t comma p. Here it gets replaced by t comma ft of p. Okay. So then I get a new volume preserving flow, which, and we call this operation plug insertion, and we denote it by phi t sharp ft. That's this thing here. Okay. So in this way, you could start off with a volume preserving flow, a smooth one or non-smooth one, and create lots and lots of other volume preserving flows. And of course, the question here is, how does this affect the helicity, this operation?
Is this just conjugation by homeomorphism of the cylinder, which is ft at each time?
Sorry,
Can I use it as a conjugation in the space?
Maybe, I'm not sure. I mean, if you want, I can explain what, do you want to explain this part again?
Yes.
So, look, the flow lines here are of the form t comma p. T is the variable that's pointing in this direction. Then I replace t comma p with t comma ft of p. Where ft of p is this isotopy of the disk. At every slice at time t, I have an area preserving map of the disk, and I apply that at time t. Conjugation.
Yes.
I mean, there is some conjugation. Yeah. Okay. So what's the connection? How does this affect helicity change? So if everything is smooth, the change in helicity is exactly given by the Calabi invariant of that, the time one map of that isotopy. And that was proven by Gamma-Dogis in their 97 paper. Okay. So we construct our helicity extension so that this identity is satisfied in the C0 setting. Okay. So what do we do then? We fix a choice of a Calabi extension. There's lots of them, but you pick just one. And then using that, we extend helicity, keeping in mind that we want this identity to hold, this Gamma-Dogis identity, we want it to hold all the time. And it turns out you could do this, and that actually uniquely determines the helicity extension. So once this choice of Calabi invariant is fixed, there's a unique helicity extension which satisfies the Gamma-Dogis identity. Okay, and okay, so in this way you get actually lots and lots of helicity extensions. So, okay.
Can you also use this kind of universal extension with value in sequence modulo something?
Yes. Okay. I was okay. So since you mentioned it, that's on the bonus slide. I'll show you that. Yes, you could, if you want to avoid the axiom of choice. I wasn't going to mention this, but now universal extension. There is an abelian group. It's not that sequences group that's the universal extension. There exists some abelian group R, curly R, and a map, a homomorphism in that group that's an extension of helicity in the sense of this commutative diagram. Okay. And this is we call the universal extension because every other extension taking values in any other group takes values. It factors through this extension. So this is part of the proof that we worked out with Edmire.
Isn't it just the abelianization?
That's what I was saying that on the next slide, right? And so if you use this construction, then you get a universal helicity extension that takes values in that curly R, and everything, any other extension you have factors through this universal extension. What's the curly R? It's the abelianization of, I mean, in this setting, the most natural canonical object that exists is abelianization of area preserving homeomorphisms. And that Calabi extension is just a quotient bound. And if you're wondering how the real line comes here, well, that's because it is known that the real line is the abelianization of area preserving diffeomorphisms, and the Calabi invariant gives the isomorphism. And how does this, okay, so where does this column come from? This is the Weyl. The Weyl gives you the fact that the real line embeds as a group inside that kernel. Okay, I've gone past where I wanted to go. There is something, a surprise I have for everyone, but maybe I'll stop here for some questions and then you'll have an immersive artistic experience. Before cookies.
Are there questions?
This is not a question, this is a suggestion. Long time ago, Dennis Sullivan made the following observation. If you look at the helicity as a function on the Lie algebra of vector fields with zero divergence on the tree sphere, this looks like the killing form on this infinite dimensional.
Yeah.
Can you make sense?
In a topological setting.
Can you define, can you define the killing form on this infinite dimensional Lie algebra, which would give some understanding of this helicity?
Of this helicity extension. Okay. Thank you for the suggestion. Keep it in back, my Yes.
So here, you see that there are big abelian curve. Can anything about
This is
nilpotent?
so you mean elements that say square to zero or something?
I mean, a curve in which your group extension by something commutative, by something. So second half group, for instance.
Do they have?
Is the half group equal to the second half group?
We've looked at this, right, Dan? Do you remember the?
Well,
Okay.
I don't
Actually, I don't
exactly this question, but we've drilled down quite a lot into the algebraic structure of this group, and it's kind of a mess.
Okay, so actually, maybe I can give you a short answer. I noticed the group is abelian. Beyond that, we know there is a natural group homomorphism from the real line into it. And beyond this, we know nothing about this. That's kind of like.
We don't know it's divisible.
Yeah, if that's what you were asking, we don't know if it's divisible or torsion free.
Go deeper to look at the kernel of this map, and is that simple, for instance?
That we also know.
No, the kernel of this map.
Yes.
So that's the commutator subgroup.
Yes.
Yes, it is known that's simple. So that answers your question. Right, right. So that is simple. Right, because this is the universal extension. The previous Calabi extensions, we proved they don't have simple kernel because the commutator subgroup is. The fact that the commutator subgroup is simple is some sort of a universal argument that goes back to 60s or 70s, to Mather. Okay. That I think was known already way back. And this universal group is, one needs to understand it, but I don't.
Say, did the people in fluid dynamics ever consider continuous extension? I mean, having definitions for flows which are only continuous rather than this very weak definitions.
As far as I know, no. I was hoping to talk to Camilo about this, but actually, so I don't know. But we're trying to talk to the Giri and Kwan. In fact, we have like a mini conference in 2 weeks that we're hoping to talk to each other and understand.
Did you invite the president?
The president of ETH-Zürich? I think he might not become very happy if he sees. We have an explanation for him, of course, if it comes. I don't think they've considered, I mean, from what I understand, they're concerned with vector field. I mean, that's where the Euler equation makes sense. Can one make sense of the Euler equation for flows that are?
I think Dennis Sullivan tried for many years. to
Yeah,
convince people from fluids. It could be interesting, but nobody listened to him.
Yeah, but that
maybe
gives
now we will try.
some more weight to such a viewpoint.
Yeah, okay, we'll try to discuss it one another, but these guys are really hardcore analysts and so. It's a good thing, but there is some barrier at the, we have to get past some initial barrier, which we hope to do since we're at the same department.
Okay, and then you wanted to show us an immersion.
Yes. So it turns out, so Sam, you told me I do command. Tab?
Yeah, tab, sorry, you're right.
Aha,
Press spacebar.
and spacebar. And the volume we can turn up, or, so maybe I'll.
Volume should be up.
So what you were looking at is a work of art created.
Homeomorphisme de la sphère de dimension 2.
You recognize the voice?
Et l'orientation.
So it turns out that in.
Préhistoire.
So it turns out that, or maybe I'll let you explain, since you were a collaborator on this artistic creation.
The explanation is the following. A few weeks after I gave this Bourbaki seminar, I realized that the artist had at the Paris, the title is diffeomorphism. I discussed with the guy. I said he understands. He likes to take a mathematical paper and deform it by diffeomorphism. So I discussed with him, and then he said a few days later, he asked me, would you record your Bourbaki seminar? And I will deform both the voice and the text. And this is what it is.
This is Atkins Bourbaki talk on simplicity question. This is the artist's attempt at his artistic impression of an isotopy.
Yes, so
As we see some minor points like the Euler characteristic changes. So it seems like this simplicity question is, not only has it been inspiring to mathematicians, but also to artists, thanks to Etienne.
Yeah. Thank you very much.
Thank you all. Thank you.